Recording. Welcome to the last, brown bag science luncheon seminar for this year. We'll start again next fall. Please make sure you sign the roster that's going around. The university likes us to account for all the mouths that we feed, and it's hard for us to make it up when we get back if you don't sign that. Where is it right now? Right here. Sign that. This luncheon is sponsored by the Utah Cooperative Fish and Wildlife Research Unit, a USGS function, in partnership with the Utah Division of Wildlife Resources, and I'm Peter Booty, the unit leader, in case you don't know me. And it is my pleasure today to introduce Dr. Ed Hammill. Ed is an assistant professor at Utah State University in the Department of Watershed Sciences, my home department. Ed has been doing a lot of work on the topic that he's going to talk about today. He was previously employed as a research fellow in the very prestigious Hugh Possingham's Environmental Decisions Group at the University of Queensland, and he remains associated with the Center of Excellence for Environmental Decisions and the National Environmental Research Program's Environmental Decisions Hub. He is head of what he calls the Spatial Community Ecology Lab at USU, where he and his group have been doing a diverse research program addressing fundamental questions in community ecology, ecosystem function, and topical applied issues. And today, Ed is going to talk about systematically identifying priority management areas in terrestrial and aquatic ecosystems. And this has been a niche that we've been really pleased that Ed has been able to sort of make his own with lots of application to issues in Utah and beyond.
Okay. Thank you, Freda. Thanks you all for coming. It's good to see a few familiar faces and a whole bunch of new ones. So yeah, today I'm going to talk about some of the work we've been doing at the lab over the last year or so. I've heard that humble brag is not trendy anymore, so I would like to say that a lot of this work was put forward by Jeff Haight and Andy Witt, who's two of my students actually at the lab. But as humble bragging is no longer trendy, I supervised them as all my idea. Don't listen to a word they say. But without these two guys, a lot of it really wouldn't have been possible, and a lot of the work that I'm talking about today has been spearheaded by them. And this work stems out of, the basic idea behind it is this idea of systematically identifying priority management areas in terrestrial and aquatic ecosystems. Within this, Jeff did a lot of the terrestrial applications. Andy, who's just obsessed with rivers and fish generally, was spearheading a lot of the aquatic side of things. And this project actually stems out of a partnership between UDWR, the Nature Conservancy, and us at Utah State. Okay, so if we start back at the sort of very, very beginning and right at the first principles, we have this idea where managers generally have limited resources to allocate among multiple projects. Sometimes these resources are really easy to quantify. They're things like we have a certain amount of money in a pot, we have to allocate which projects get what for the most amount of benefit, or we have to allocate the amount of money that goes to a whole portfolio of projects. If we live in this wonderful, magical, happy fairyland where money isn't an issue, we might have other things that limit the amount of work we can do, including things like time. Even if the money is available, many projects are very time sensitive. It might be that work has to be carried out before the end of the summer, before the snow comes in, or it's just the fact that we didn't have enough time to allocate our people to. In addition, we can have issues with personnel, where we literally do not have the people to allocate to every single project we would like, so as a result we have to start making decisions around that. Or in some cases there's been a call from on high that just says that a certain amount of work shall take place. For example, we shall restore a certain amount of stream miles within a river network. Even if we've got all the money in the world, all the personnel and all the time, the fact there's been this thing from on high saying this is the limit means every single stream mile you do means you can't do a whole bunch of other stream miles. So that means you have to then start to come up with that. And what this means is, because we've got limited resources, we need some sort of strategic allocation in order to get the most out of our limited resources. So for things like, if our goal is to maximize wildlife connectivity, and especially reduce the interactions between migrating deer and roads, what we're optimizing on is we have a certain amount of resources to put in wildlife crossings, to put in culverts. Where should they go in order to maximize connectivity? In addition, when people are deciding where to do things like restoration is really expensive, especially aquatic restoration. So as a result, you need to identify where on the landscape am I going to get the most amount of benefit for the certain amount of resources that I've put in. So what we need is some sort of strategic allocation framework in order to get the most out of what we have available. And this can be done using a whole area called optimization and theories that are originally grounded in economics. So these sort of questions, how do you get the most out of a certain amount, or how much does it cost to achieve a certain thing. That's been done in economics since the year dot. There's been an awful lot of research and work going into how should investments be allocated amongst multiple opportunities in order to get the most return on investment, how best do you minimize risk of your total investments failing, all that sort of thing. And this sort of interaction between optimization and economics was really, really heavily sort of illustrated to me when I worked at the University of Queensland, where at that group they used to keep on staff at least one burnt out stockbroker permanently. Because he basically, the head of the group, Hugh, had worked out there's this enormous group of people who often are very, very cash rich, but don't like their job, want to live somewhere beautiful, and he lived in Queensland, in Brisbane, one of the most beautiful cities in the world. He basically said, if you work the absolute minimum you need, I will give you an Aussie visa permanently, and you can come and live here, and then he basically paid them for about a day's a week worth of money. So this idea was put into me that a lot of the things that we end up using, or end up getting used in wildlife management, some of those ideas have been in economics for a very long time. And so the first question you have to think about is, what is optimization? You'll often hear these ideas saying people saying things like, optimization is the goal to maximize outcomes while minimizing the resources that we put in. So for example, if we've got a situation where we're trying to increase fish spawning habitat in the river network, we want to make the maximum amount of fish habitat for the minimum amount of money going in. And that is not right. So if you hear people saying that simultaneously going to maximize outcomes and minimize resources, you might want to start being a bit suspicious, because that's something where you're pulling in two different directions and it becomes impossible to find an optimal solution. What you do instead is you set some sort of target or limit, and then you maximize the resource, you minimize the resources you need to achieve that target, or you maximize the outcomes you can get from that particular limit. So you fix one and then optimize on the other. Okay? So questions like, where should we place crossing structures to maximize wildlife connectivity for a set amount of money? That is, we've set a limit on the amount of money we can spend. Where do we put things to maximize the total amount of connectivity? We've set a limit and we're optimizing on the other. Alternatively, you can have things like, we need to minimize the amount of money that we have to spend that's needed to restore 50 kilometers of habitat for riparian and spawning fish. Okay, we've set a target. You set a target of getting 50 kilometers of habitat. How do you do that in such a way that it costs you the least amount of money? Okay. So both of those things you can see, it's a slight twist on this maximize and minimize at the same time. It's you set one and then optimize on the other. Okay. If you hear folks talking about how they're going to maximize this and minimize at the same time, immediately be a bit suspicious. And since 2016, my research group has been working with UDWR and TNC to answer a little suite of optimization questions as part of a larger project we've been doing. And some of the questions have revolved around this general theme of how do we minimize exposure to climatic changes in terrestrial and aquatic species. So the basic idea we're trying to work at is we have this thing we want to minimize, which is exposure to climate change. We then set a whole bunch of targets and we start to run the optimization. And what we'll talk about today is some of the general principles behind this, some of the results we've got so far, the general ideas, and also looking at some particular species of interest. And when we're talking about exposure to climate change, we've done two different things. One of them is the actual how much change does an individual species experience or a place experience. And the other one, which we'll touch on a bit today, is focused on connectivity. So how do predicted changes in climate, how are they going to affect the ability of species to migrate across landscapes, and how are they going to alter the connectivity of focal places of interest? And what we'll talk about right at the end is this idea about how, unfortunately, sort of climate issues are not the only things that wild habitats are facing at the minute. So we talk about how we can combine issues regarding climate with issues regarding things like development, encroachment, and things like that. Just like to reiterate this project involved no collection of new field data at all. There's an awful lot of data available. The data that what we've done today is literally using existing data sets and putting them into a decision framework. This was kind of interesting when I was asked to provide a picture of me in the field, because this has absolutely no field work component to it whatsoever. So I sent you a picture of Tasmania, so well done everyone despite that, which I thought was about as far away from Utah as it's possible to get. So we've got no new collection of field data. Everything that we're doing is taking existing data sets, things that are available, and trying to get a bit of value add out of stuff that's already been collected. And so, for example, some of the data sets that are available now are pretty extensive. So the UDWR-USU database has got a fantastic resource for data on climate variables, both today and into the future. It's freely available online, and anyone can download it. In addition, as part of this project, we provided data sets from DNR and from Trout Unlimited regarding distribution of some species. So there are these large resources available, and it's possible to actually do quite a bit of stuff with what's already there. So the first question we sort of touch on is, how do we minimise exposure to climate change for terrestrial species? So if we start from the principle of saying, well, even saying it's predicted that climate will change in the future is a bit of a misnomer now. We have observed it changing quite a fair bit. It's generally predicted to get a bit hotter, about a 1 degree change what's been observed so far, and we're going to get change in the distribution and allocation of precipitation as well. Also, Utah has an awful lot of very quite charismatic and in some cases species of management interest. These are very cute, as are these, and these cause a fuss. So as a result, we've got this situation where we've got changes in climate, and we've also got, I've never seen a desert tortoise. Is that a desert tortoise?
Yeah.
Perfect, okay. I just Googled desert tortoise and hoped against hope it actually was one. I love the fact that that particular animal seems to have the power to have such a large impact. The fact that a lot of decisions regarding grazing and stuff like that can evolve around such a great little herd is wonderful. But so this situation, we've got a lot of species of interest. How are they going to get impacted by climate change? How can we then actually make decisions relating to these species that minimise their potential exposure? Well, the first thing we need to do is get hold of some climate data. As I mentioned, there is a fantastic data repository with the UDWR-USU database. That can provide a 1 kilometre squared raster for all of North America. It can give you data on what the climate is right now, what it's predicted to be in the future, and what it's predicted to be in the future under a whole series of different sort of CO2 emission areas. The database contains up to 27 different bioclimatic variables. They relate to changes in temperature, changes in precipitation, timing of rainfall, timing of ice melt, all these sorts of things. And they can actually be broken down into 48 different monthly variables. So there's this enormous repository of data freely available to anybody that wants it. The issue with this is the data when we first get it isn't in a particularly usable format. It takes quite a bit of playing with in order to get something useful out of it. Fortunately, my student Jeff, one of the products that he's produced out of this project is a whole series of maps relating to Utah, relating to how its climate's going to, the actual magnitude of how the climate's going to look like. He's clipped these down, and he's also developed a whole suite of R scripts that can be used. Anyone can take them on, and you can just tweak those a little bit, and it'll suck the data out of the database for you and provide you the maps you need. Okay? So although this repository exists, it does take a little bit of playing. Now the issue with this is that this data, it just tells you what the climate is in a particular place now and what it's likely is going to be in the future. And that's not how animals and plants react to changes in climate. They don't just sit there and cook or dry out. Instead, they migrate, they move across the landscape. And climate migrations have already been observed for a whole suite of species. For example, the poleward migration of bird species has been seen in the US between 1966 and 2013. So if you take the centroid of where our bird populations exist, so you take all the birds in the US and work out the middle point of where the highest bird density is, I learned how to do this the other day, that's actually moved up north through time. So when species are exposed to changes in climate, they don't stay still, they actually move across the landscape. So as a result, the way that they're exposed to climate change is not the absolute magnitude of change they feel in one place, it's how far do I have to travel in order to maintain what I'm being exposed to right now. And we can do that using this metric called a climate velocity. So a climate velocity is another measure of exposure to climate change. And what it is, it's saying how far and in what direction and how fast do I have to travel in order to stay in the same climate that I'm at now. So what you do is you get two rasters of your climate data. If we on the bottom, this one is the current climate condition, this one is the future. And what you do is you say for every single pixel on the landscape, you find the climate envelope, you then find that exact same match, so a pixel has the same climate in the future, and you work out how far do I have to travel in order to maintain that climate envelope. So it's what speed and what distance. So what it is the climate velocity is a measure of how far something has to travel in order to stay in the exact same climate condition that it is right now. And you can define these in a whole bunch of different ways. You can make a climate velocity based on just one variable, for example, mean annual temperature. You might sit and say, right, I'm at this place right now. Given the predicted changes in the climate, where is the nearest space has the exact same mean annual temperature as where I am now? In what direction is it? Okay, if I go over there, I don't actually feel any change in climate, I just have to move across the landscape. You can do it with one single variable, or you can do it with a suite of variables. You can say, at present, in this particular area I'm in, I know there's the mean annual temperature, mean annual precipitation, day of ice off, all this sort of fun stuff. Where in the future we'll have that same climatic envelope. And what you can do is then turn that into a metric that gives you a better measure of exposure for your area. So this is what it looks like. This is data coming out from Jeff. This image is climate velocity based on temperature. This is it based purely on precipitation. And this is it based on both at the same time. Okay? What you can see straight away is on all of these, the red is a very relatively high velocity. That's when a species has to travel a very long way in order to get the same climate envelope. Blue is, it doesn't have to travel hardly any distance at all. Where it is now, in the future, there's going to be somewhere very, very nearby that has the very similar climate. If you look just at temperature, what you can see first of all, the places that stand out are, the places that are very red are the tops of mountains. The reason for that is, if you're on the very top of a mountain and the climate changes such that it gets a little bit hotter, the easiest thing to do if you're on a mountain is go up the mountain a bit more. If you're on the top of a mountain, the nearest place that has the same climate in the future could be the next highest mountain, which could be in a totally different range. As a result, if you're right on the mountain top, you eventually get potentially pushed off the top. Conversely, if you're lower down, you only need to go up altitude a little way in order to maintain your climate envelope. So those steep parts of the mountain might be very good places to work. Rainfall looks very different. It seems that the sort of there in the West Desert seems to be the bit that's going to experience the most amount of change. Everything over here looks a little bit easier. When you combine both together, remember in this case, now it's looking for a match, not just for one or the other, but for both. So you have to find a place that has the same temperature and the same rainfall. The pattern's almost an amalgamation of the two. Okay? But what's crucial about these is there's very little spatial overlap among different climate metrics. So if you look at the pattern when you're in temperature compared to the pattern on rainfall, some of these areas that are very red here, very blue here. And what that means is if you're trying to make decisions relating to a particular species of interest, it's absolutely crucial that you know which climate parameter is determining its range. Because if you pick the wrong parameter and you say, right, we'll go to the places that represent climate refuges, you're going to end up with something potentially very, very wrong indeed. Jeff actually went and quantified this and actually looked at the percentage overlap between climate velocities based on two different metrics. So this is temperature versus rainfall. I don't know why I couldn't understand that for a second. And you look at the percentage overlap for each of the different quantiles. So this is the lowest 10% climate velocities, the next 10, the next 10, the next 10, the next 10. And what you can see is that level of overlap is absolutely tiny. It tends to be about 10%. So that means, if for example you're saying, right, I've got the climate velocities based on temperature, and I want to find where the minimum areas are, and I'm going to focus on those to do management actions for species of interest. If that species distribution is actually being determined by rainfall, you've got less than a 10% chance of actually being in the right place. It's really, really crucial to understand which is the important metric. Also, the climate metric being used actually determines overall velocities. This is the mean or the average velocities based on temperature, rainfall, and both. You can see that if you look at mean annual temperature, the mean velocity you have to travel, the distance you have to travel, and the speed is a little bit higher than with rainfall. But if you're trying to match both, the distance and speed you have to travel is an awful lot higher. This is, if you think about it, reasonably obvious because now you're trying to match two different things rather than just one. So while we can do this, and Jeff has produced these maps of the entire state, you can also do a system where we've got a process where for a particular species of interest, you can actually build a bespoke map based on the ranges and the limiting climatic parameters for that species. So for example, this is Elizabeth milk vetch. Spatial extent was got from Tom Edwards as part of his Rare Plants project. The reason I picked this is because Tom likes it and it's a pretty little flower, and its species range looks like a shark, and so it just makes it instantly more fun. And you can crop out the distribution of that species, and then within its distribution, you can calculate the climate, look at the climate velocity and say, right, any management action we want to take for this particular species, let's focus on the areas where the climate velocity is low, because it's likely that that area is going to be relatively unimpacted by future changes, and it might mean the action's a bit more resilient to future events. In the absence of any other information, we can just take an approach where if you focus on areas of minimal climate velocity, it increases the chance of a long-term success in any actions you take. It means that any actions that are taken in terms of restoration or mitigation, if you go to these areas where there's minimal exposure to potential climate changes, it means that any actions you take might persist into the future a bit longer. It's just a bit of a bet hedging exercise. However, the goal of this, the idea about this aspect of the project is to identify where are areas on the landscape that we might prioritize management actions so that they've got a long-term future chance of success. But it's all based on abiotic parameters. It's literally you're measuring temperature and you're measuring rainfall and then saying, right, that's going to be everything sorted out. And identifying management areas based entirely on climate velocity misses one crucial factor, and that is the actual wildlife themselves. You might be able to identify climate refuges, you might be able to identify areas where things are going to be relatively resilient to change, but if nothing actually lives there, it's not necessarily a particularly valuable place. I just picked these because they were charismatic again. So, if our goal is to actually manage wildlife, we probably should include wildlife in the optimization process somewhere. And so, this is something that we worked together at a late part of last year about how do we start identifying low climate exposure areas for multiple species simultaneously. So now rather than saying where is a climate refuge on the landscape, we want to try and bring in species ranges at the same time. And the issue with this is it's then we need to make a multiple objective solution. We're simultaneously trying to fix things for multiple species at once while minimizing one metric, which is our climate velocity. Fortunately, there is this great optimization tool called Marksan, which can do these sort of ideas. The way that you work Marksan is you set targets, you set what you want to achieve. The tool then minimizes a value, in this case, climate velocity, subject to meeting those targets. The nice thing about this tool is also it's quite universal, and you can include other things such as the risk of projects failing due to other reasons. And the way it works is you start off with your basic landscapes. This is the cartoon of my landscape. We have the distributions of our features of interest, such as the ranges of different species or the distribution of a particular habitat we're interested in. We then put a grid of planning units over the top, and these planning units can either be just a grid you overlay yourself, you can make a little thing yourself, or you can just use natural landscape barriers, such as Part 12 watersheds and things like that. What you do is you then take, for every one of the grid cells, you parameterize the area covered by the range of each different species or feature of interest. You then add the climate velocity for that particular cell, and you can also bring in the risk of failure due to outside problems. What you do is you just then press go, and it identifies a suite of planning units on the landscape, and it says, these planning units are the places that represent high priority management areas because they achieve your targets for the lowest climate velocity. Jeff actually ran this using a case study for the Southern Rockies LCC. The Southern Rockies it was chosen because it takes up a natural barrier rather than a man-made one, and includes parts of 4 states. In fact, no, it's more than that, isn't it? It's got bits of Idaho and that. And what Jeff did is, first of all, calculated the climate velocity for the entire Southern Rockies LCC based on temperature and precipitation. So this is a velocity where it's trying to match in the future areas both for the mean annual temperature and the mean annual precipitation. This is what it looks like overall. This is there's the 4 corners, so we've got the different states, which I won't try and name because I'm embarrassed about my geography. And then we have the general climate velocity. Red is very high, high exposure areas. Blue, very low, low exposure areas. Just at the very beginning, you can see straight away there's an awful lot of spatial heterogeneity. We've got some very blue areas, very close to some very red areas. This is actually good because it means it gives the optimization algorithm a lot to work with. If you've got a situation where you've got some very high and some very low, and they're spatially close, that's good. The worst situation is if everything looks totally exactly the same. We then built a suite of targets to actually manage, which were based on the distributions of species. These were the distributions of 31 species of concern, all terrestrial species, and they're identified based on the IUCN status, so whether or not they are critically endangered, vulnerable, or near threatened. This is what the distribution of them looks like in a sort of relatively simple way of doing it, where this is the species richness. Darker areas mean it's got an awful lot more of these species present on the landscape, lighter, not so many. And the goal, the target that was set, was to manage 20% of the distribution of every one of these species simultaneously. So the overall goal is to identify areas which represent places where management could be targeted that would help 20% of the distribution of these species for the minimal overall exposure to changes in climate. At the same time, you can also include risks of management actions or things on the landscape failing. The way that the risks were included here was based on the percentage of developed land cover. This worked on the principle that if there is a cell of the landscape that is in the middle of a city or it's high-value agricultural land, it's unlikely to be managed exclusively for wildlife in the future. People aren't going to do that in the middle of downtown Salt Lake. This is what that looks like, and you can basically see the urban centres and some of the high-value ag land in there. So the goal then is to identify areas that minimise exposure to climate change for a whole portfolio of species simultaneously. So you take the distribution of the species, minimise the exposure to climate change, and simultaneously account for these other risks on the landscape. This is what it looks like actually at the end. What we do is we run this markdown analysis hundreds of times, and every single time it picks out what it considers important cells. We look at how many times each cell was selected in those different runs, and it pulls out the really high value areas. This then gives it the prioritization. The dark blue areas are really high value. The light green are considered slightly less so in this analysis. And again, what we can see if we zoom in is that this is the prioritization based on the Markdown analysis. This is just the climate velocity, with blue being very low exposure, red being very high. And you can see it is picking out these low exposure areas, but it's not picking out all of them. So what this is helping do is it's helping narrow the potential range of options. If we focus just at this, you might actually end up identifying some areas which possibly could not be massively useful, because although they're climate refuges, they don't contain the species of interest. This combines it both together. And as a result, you can really focus on the areas not only where the species are, but in theory, where any action is going to be relatively immune to future changes in climate. Now that analysis was done purely on exposure. All we're trying to do is minimise the overall exposure of a whole portfolio of species to changes in climate. You can actually flip the analysis slightly, and rather than focus on minimising exposure, you can focus on maximising connectivity. So this is, again, the map of the Southern Rockies LCC. And this time, the heat map describes where in the future, according to climate changes, are going to represent least cost paths so that species can move across the landscape without experiencing massive fluctuations in temperature. And the goal was to connect together a whole bunch of areas such as national parks and wilderness areas, places which are currently wildlife priority locations, and seeing how with future changes are there going to be paths that can connect these together. So the overall goal was to identify areas that will connect current wildlife management areas given climate changes. Using connectivity maps and algorithms, we can identify potential areas that species might use as wildlife corridors. However, what we can do is take the state we are at now, see what the future climate is going to look like, and rebuild those maps and see how these connectivity corridors will change. And what we can do is then run these same sort of analysis that we did in Markstown, where if we base it on minimizing climate velocity, which is just exposure, we can also run the same analysis where we try to maximize climate corridors, so trying to maximize movement rather than minimize exposure. These are the two maps on the same scale, and it can show the differences in the spatial areas. So for example, if you focus on the southern part of the Southern Rockies LCC, this, if you base it purely on exposure, is considered this area here is considered relatively low priority. If you base it on connectivity, because there's already these existing wildlife management areas, and there's potential for species to move backwards and forwards between them, its importance is actually increased. What you can also do is combine these two maps together, and any map that has a spatial overlap, for any area that has a spatial overlap and is high in both, then represents potentially a very high priority region where not only is it relatively unaffected by future changes in climate, it also represents an important point through which species can move backwards and forwards. Okay, so the big goal about this whole approach is this Markstown framework essentially narrows potential options for where work might take place. What you can do is you can identify areas that provide resilience to climatic changes of multiple species and areas that represent important trading posts where things can move backwards and forwards. So, essentially the goal, this part of the project describes how if you're given a whole range of different options, how do we start to identify where actions could take place? Now, one thing you might notice about this is all of the stuff I was talking about was, this is my big break, nice charismatic picture to bring everybody back up to speed again. But everything was based on terrestrial landscapes. It's all about how species move across landscapes. It's all about how climate exposure affects the terrestrial realm. However, I'm in the Department of Watershed Sciences. I've been told to keep an eye on rivers and things like that as well. I understand that water is very, very important in the West. We've got some very, very beautiful places in Utah, so we probably should be having a look at these as well. The issue with rivers is that there's some extra considerations we have to take into account. So one of the big things is that rivers have a linearity, an upstream and a downstream. It flows from upstream towards downstream. As a result, any threats or exposures that an area is receiving might compound as we move downstream. Also, a lot of the algorithms that we've been using, they base a lot of stuff on nearest neighbours. So you have something here and something nearby, those two are really close to each other. In the aquatic world, adjacent locations might not actually be connected. These two, for example, these two watersheds here are adjacent to each other, but are not connected at all until we get right down here at this nick point. So if we were to use a lot of the ideas that we do for the terrestrial realm, it might start saying, oh, well, there's a corridor here, which there clearly isn't. So you have to try and include some of those aspects. In some cases, for many species, movement, because there's linearity, might be easier in some directions than others. For aquatic insects, it's much easier for them to drift downstream than it is for them to crawl upstream. They can, as adults, fly and potentially go back. But during the aquatic phases, which some of them last like that for years, it's a lot harder to travel up and down. And these are things that have to be considered. So Andy Witt developed this framework whereby you can actually use the FAFSTEDR coding that's present within rivers, so whether something is a first, second order, third order stream, can be used to calculate how exposure to things like temperature changes as you move through a watershed. So this, for example, is the Logan River watershed. Based on these FAFSTEDR rules and the predicted changes in temperature that Jeff developed, Andy developed this system whereby we can see how exposure to climatic changes compounds as you move downstream. So if you start up in the headwaters, you can see there's an awful lot of blue, which is a relatively low mean risk of temperature change up in the headwaters. Down the main stem, it gets much higher. And this is because of a couple of reasons. One, any water in here has been exposed to the compound of all the exposure that happens upstream. In addition, anything that's down low, it's been flowing for a long time, it's had a lot more time to be affected by things like evaporation and stuff like that. So as a result, generally, the risk compounds as you move downstream. You can input that into the entire state. I know this isn't the most easily interpretable figure in the world, but what we can see is if this is the Logan watershed, it's been thrown into roughly there, I think is where Logan is, but Fade will tell me I'm wrong in a minute. And then you can see there's a lot more red up here in the northwest, there is in the southeast. To represent this at the state scale, it's actually easier to take the mean exposure to change within a watershed and represent that, and then it looks a bit like this. So this is the Huck 12 scale, and slightly clearer patterns emerge with respect to exposure to temperature changes. Yet we have an awful lot more predicted change occurring up in the northwest and down in the southeast. What we can then do is take these data, and in the same way that Jeff did with climate velocities, actually start to use this as a metric to try and minimise when we're looking at aquatic applications. But for aquatic ecosystems, there's an awful lot of other risks present on the landscape. So environmental risks are a big deal, and this was really highlighted by the National Fish Habitat Action Plan. It basically showed that although climatic changes are going to be an issue at some point, there's also lots of things in the landscape that are happening here and now. Population and development, especially in Utah, with the fastest growing state in the union. There's an awful lot of people coming into place and being produced here. In addition, agriculture often represents a threat to river systems. Mines and tailings and grazings also can have impacts. So the National Fish Habitat Action Plan put together a whole series of data about how these risks are present on the landscape. Andy was able to go ahead and turn that into a spatial map and produce this map of the National Fish Habitat Action Plan of 2010 and converted all of these risks into what's called a human disturbance index, where for any particular watershed, you can calculate the disturbance index ranging from very high to very low. For the state of Utah, around the middle of Salt Lake City, you've got a high disturbance index and some of the agricultural land up north. But again, what's interesting is there's very highly disturbed areas and very relatively low disturbed areas very close to each other. And again, this gives lots of room for optimization. So Andy and I got together and said, well, we can actually combine the temperature data that was produced from the fast weather rules and these disturbance risks together into one metric to produce a combined risk score. So this combined risk score is the risk that any watershed is impacted by either temperature or disturbance or both at the same time. And you can use that and then apply it for different watersheds. Because this is then a single metric, given here, so it gives it between 1 and 0, because it's a single metric, in the exact same way we did before, we can set targets for something and then optimize to minimize the exposure to this metric given our set targets. And so Andy actually set about doing this for cutthroat trout in Utah. The goal was to set management targets and then optimize to meet those targets for a minimal combined risk score. So got hold of the data for Bonneville cutthroat trout and Colorado River cutthroat. This was provided to us by Trout Unlimited, which was very nice of them. We were also able to find that UDWR has some set objectives for how much stream miles are meant to be managed for both these two species. So it's 294 stream miles for Bonneville cutthroat trout and 537 stream miles for Colorado River. So we have these targets, and we can then convert these and try and meet, how do we then look at meeting these targets for the minimal exposure for the combined risk score. Andy went and did this, and he set aside, the idea was to identify the Huck 12 watersheds that meet UDWR targets for the minimal combined risk score. This is what it ends up looking like. It meets the objectives, and the mean combined risk score for both these species is only about 20%. So that means, on average, for any one watershed that you're looking at, there's only a 20% chance of it being impacted by either temperature or development, things like that. The interesting thing about this was the headwaters, the Ogden, Provo, and Weber, just kept on coming out again and again and again. This is what that area looks like, and it looks like, from the sort of back of the envelope calculation of what Andy did, achieving the UDWR targets may be possible with only using about 10% of the species that coexist with non-native fish. So this, I thought, was quite a nice result. So, just like to summarise this by saying, this idea about exposure to risks can be used as a metric to be minimised in optimisation analyses. Generally in optimisation, we're trying to minimise one particular component. For example, in economics, we might kind of minimise the risk that our investment fails. We can basically take that whole idea and transfer it onto a landscape and say, how do we start to do these management actions while minimising the risk that they're going to be impacted by future changes or development? You can do it for a single species, such as the Elizabeth milkvetch. You pull out its distribution and you see where it exists in the landscape and focus on the places that are less likely to be impacted by change in rainfall. You can do it for a suite of species simultaneously, and you can even do it in aquatic systems, taking into account the linearity of rivers and fun things like that, and also multiple risks in the landscape. This project is actually coming towards the end, so we've got a whole suite of deliverables that have to be given in at the end of this month. The report that's coming in is also going to include all the maps we've produced, the R code and the frameworks for how to do things in either R or ArcGIS, and the report itself. This is going to get delivered at the end of this month. This will include all the climate velocity maps, all the connectivity maps, and also the combined risk maps and things like that for the aquatic work. We're also keen to actually run an instructional workshop in July. So if anyone is keen on learning how to do things like the climate velocity calculations or the connectivity calculations and some of the basic incorporations into Marktan, Jeff and Andy, they're here till the end of till the beginning of August. One of the big deliverables we're doing together is actually sitting down and running a workshop to show people how to do some of these basic ideas. So, because it's coming to the end, we've been thinking about where do we want to go next. So, one of the things that was identified in Andy's work especially was the importance of the Weber, Provo and Ogdens. Although it identifies these watersheds, it doesn't say what to do within these watersheds at all. It doesn't do any of that sort of stuff. And it's very broad scale. It doesn't focus on a mile-by-mile basis. Some of the work, and especially some of the reading we've done, there was a student who was with Sarah Null, and I think was she with you as well, Maggie? Yeah. So with Sarah Null, who was looking at fish barriers and how fish barriers impede movement of cutthroat. While they do impede migration, they also do prevent or reduce the probability for mixing with non-natives. So what we started to look at is see whether or not some of the optimization ideas we come up with can be applied to the same idea. Courtesy of Trout Unlimited, it looks like fish barriers in Chalk Creek have been very well mapped indeed. And we also found there's a tool called the Barrier River Optimization Toolkit, which is designed specifically to identify barriers that can be removed in order to achieve set migration targets for minimal risk. So our idea is we can take this essentially off-the-shelf tool and we can ask it the question of, we want to set a target of the total amount of migration we want trout to be able to achieve. How do we remove barriers to achieve that migration while minimizing their exposure to other threats on the landscape? And the risk that we've thought about, courtesy of what Andy's produced, is, well, this risk can include climatic changes and how they can directly affect trout. Also, the risk of non-natives. Every time you move a barrier, you might get a non-native coming in. And also, how climate change affects the distribution of non-native species. So we've spoken a little bit with folks at Trout Unlimited, and they've talked about this idea that with changes in climate, you might have range shifts to some of these non-native species. This can actually be something that we can try and put in. This tool was actually developed by the United Nations Environmental Programme in partnership with Fishworks and the University of Kent in the UK. We spoke with those folks. They've been very happy to provide us with the tool and all the stuff to actually make it go, which was very nice of them indeed. When we spoke to them about it, it was designed specifically for use in the Great Lakes ecosystems with the exact same situation. So they've got a whole bunch of barriers that impede fish migration. They've also got an awful lot of threats that are present in the Great Lakes. So this tool was developed to see how do we start pulling things out in order to maximize or achieve a target of migration while minimizing the risk of different species. And with that, I'll call it there and just ask for any questions.
Question, with your multi-species optimization, how are you using the range maps to determine the exposure? Are you using a single exposure for each species?
No, so
Like, or how are you? Those ranges encompass a wide range of velocities.
yeah. So within the range of every single species, it is overlaid on the landscape, there's also the climate velocity overlay of the landscape. So within the range of that species, some areas of its range will experience very high velocities and some areas will experience very low velocities. What the tool is doing is it's picking out the areas within its range that are very low velocities. And it's also where the ranges of multiple species overlap, and you also have low velocities become very, very high priority areas indeed. So the only reason it can do what it's doing is because you have this situation where the ranges of the species are overlapping some high and low velocity areas. Does that make any sense?
Obviously, those range maps are extremely over-predictably broad. They're,
Yeah.
You know, including desert, mountain, everything in between.
So we did do those maps. A lot of them is taken off the IUCN spatial data, and anyone who's used the IUCN spatial data can tell you all about its level of spatial resolution. It's amazing. But Jeff has also been very good at sourcing data for other species on a much more precise scale. So he's got very good range maps for things like some of the mule deer and stuff like that he was able to just approach people and say. And with some of the stuff that's being done, admittedly right now with college work and stuff like that, that's really nice because you can not only say where do species exist, but where are they spending more time. And if they're spending more time, that is a higher, in theory, a more useful habitat for that particular species. If we're across its entire range, you see that, yeah, there's dots absolutely everywhere, but the majority of them are time they're clustered in one place. You can convert those dots, rather than being a single polygon, into a raster, and then optimize the value of that raster, rather than just present absence.
Does it, when you're modeling the movement of terrestrial animals across the landscape, are you assuming that they can in fact move in any direction?
They can move in any direction, but they are impeded by certain things. So one of the layers that goes into that optimization is it's called a barrier to movement layer. So you can do things like every single, you can acquire these for basically the entire US, and you just literally say, what's present on the landscape, how easy is it for something to move across that area. Those aren't species specific, so it does, for example, assume that a boreal toad can move as easily as an elk, which is completely untrue, but it is a way of actually getting into those levels. So it does things like, it doesn't start predicting deer move across the Great Salt Lake, and it doesn't predict things wandering to the middle of downtown, things like that. The problem with it is, it's with some species, those the sort of the barriers to movement maps are very, very appropriate. Anything that walks, anything that crawls. However, things that fly, it tends to be a little more problematic because they just shoot straight over the top.
When you're looking at migration corridors between the current protected areas like you were, did you consider, or is there a way to incorporate maybe a new protected area into that model, and what impacts that might have as far as creating new migration corridors?
You could do, we haven't, but that would be, if there's folks who've got ideas for that about where to put things, because it's literally that, the layer of what you're trying to connect together is literally just polygons of where these things are right now. You can very easily just draw a new one in by hand and then press go again and it'll do all the connection points. And the flip side of that is you can also take them away and see how things change as well. So, yeah, one of the things that, one of the applications that Jeff's really been pushing that for is working with Wild Utah and their boreal toad work, because they've got some amazing citizen science data on where boreal toad have been seen, but the distributions of them are crazy. It's like there's a big cluster here and then a big cluster here, and then when you look at the maps for predicting connectivity, it predicts the two, and then every now and again a ping goes off right in the middle, and it's just like, well, one gets sighted up there. So he's now been chatting with some of the folks, we've been chatting with folks over there and saying, we would love to give you these, because we suspect that for some of the citizen science, when people are going out, they're just not looking in these places because like no one's ever seen one here before, so it's not there. Whereas if no one's ever looked,
I was just going to point out, Nate's our aquatic invasive species coordinator, so instead of like saving things, maybe sometimes he's like, no,
Yeah.
protect everywhere, but that's not practical either, so
Yeah.
different sort of risks and costs and stuff. It's an interesting application environment that you know, probably haven't thought about at all.
Yeah.
But it's, I mean, I could see applications as well.
Absolutely.
Yeah, the one thing, I mean, I would love, especially with the aquatic stuff, when you've got the linearity to it, because you can then see how, I mean, putting in, so it seems like there's people putting in barriers, people taking away barriers, and things going on left, right, and centre, and barriers do two things. They isolate and they protect at the same time. And yeah, some of the applications for how things move around.
Freeways and checkpoints, or you know,
Yeah.
the vector is boats typically with the quad muscles and such. You know.
Yeah, I've been stopped by them a few times. So they were quite fun.
For that, the velocities you're talking about, so you're trying to find the nearest climate envelope.
Yeah.
Do you take into account the size of the target? So if you have these two raster cells that fit a very specific climate, I guess, conditions, and then all these cells around it are targeting that one, is that really?
No, we haven't. And that's probably one thing that would be really, I think, nice to actually have a look at in the metadata would be to see if you quantify the total amount of every single climate envelope, or bin it, so you say, right, you bin it into this many things for mean annual temperature, this many degree ranges, and you say, right, what's the total amount of that climate available on landscape now? What's the total amount in the future? And it might start getting to that. Because you said you could have some very serious bottlenecking going,
Right.
especially with mountains. Because if you've got a situation where you've got a mountain that's going up like this, and everything that lives around here, if it moves up a little way, its temperature will cool and it might be able to maintain. But it's also condensing at the same time. So you can end up in a situation where, the picture of the goat stood on the top of the mountain or anything, but that's something we haven't done.
So I know that you can't, when you're doing these predictions at this large landscape level, you can't, the amount of complexity that you can add in is limited. So it's pretty hard to make it mechanistic, but I was just wondering if, not all temperature change is equal. So for a trout, for example, a temperature change between 15 and 20 degrees is almost irrelevant, but a temperature change between 20 and 22 degrees is huge. Yeah, so is that something that you could somehow try and build in the future without making it overly complex?
We tried, I was involved, remember Doug McCauley, who came over and gave a talk about it. One of the things we've been trying to get going is trying to do this simple thing for coal. Coal work in a very similar situation where they go, a little tiny change is nothing much, then you go over a certain amount for an extended period and it's just catastrophic. It's not this nice gentle thing. And so the way that you can do that is you've got to do a little bit of calculation to change that temperature and essentially turn it into a more appropriate risk. So you're taking something that goes like this and turning it into an exponential. So it's fine, terrible. That can be done. I've not done it for this, but I don't see why. I mean, if you know that calculation, you can just convert the change in temperature to something like the chance that temperatures will be above this certain amount, which we know is catastrophic for this many days, which we know is catastrophic. And it's just, a little bit of conversion.
So when working with the cutthroat trout stuff, did you work with Don Wiley here at all?
I've spoken to him briefly, and I'm meant to be chatting with him in a minute. Is he around? Yeah.
I don't know if he's around, but I think you should talk.
Yeah, I remember speaking with him as well at the UDWR meeting, and he was talking about, because he had the really good data on when they had actually removed barriers, with the change in migration and showing the fish moving around, which I thought was awesome. So that is really good for ground truthing some of this stuff. So you can start to say, right, well, we've got this data on, we know how the removal of something will affect migration. So if you do have a target of increasing migration a certain amount, that then gives the prioritisation of how you can do these things.
Cool.
No, I saw that. Yeah, he was very good at his wonderful graphics. There's an awful lot of things flying about the place.
Well, he's also in charge of the migration initiative too, right?
The aquatic side.
Aquatic
So
side,
in this idea of temperature, changing temperature and how it affects fish movement and what can persist where and expansion of non-natives in the face of climate change.
Yeah, I was really happy actually that I was very nervous a bit when Andy was running these analyses. That I was like, please just let it line up with what they're already doing. Unfortunately, the overlap was huge, so I was like, okay, that's great. First of all, it's going to pass a bit of the legal test, and it's not going to
Yeah, that's cool.
concern people about it. But yeah, the big thing is, and as what Fraser alluded to as well, those analyses at the minute they run at an entire watershed scale, and especially for things like, restoration of spawning habitat and riparian, that's not how things are done. It's done at, 100-meter sections sometimes. So as a result, if we can get these sort of situations where we can dial right in and actually get really precise maps and look at these things, it'd be nice to run it and actually give it a go.
Yeah.
Just a plug for the data side, when this project is done, we do intend to host the data information as much as possible. Space allows us on our network, so there's a GIS data folder on the J drive that everybody has access to, where all of our other kind of division-wide GIS data is stored for and is intended for people's use, and this will be in a folder there on the project.
Yeah. And it was you guys' plan, so you don't need to ask me in any way, shape or form. I'm happy to be led.
Here it is.
Yeah, which would be great.
All right, it's after 1, and I know some people have to leave. Let's thank Ed again, and I'm sure he'll hang around for a few more minutes if anybody's got some more burning questions.